Okay, so hello everyone. My name is Gelo, and I was a participant in AstroCamp in 2020. Unfortunately, it was online during the whole situation back then, but I managed to visit the camp last year, and I really enjoyed it, even though it was just for a few days. Currently, I finished second year of university. I study physics and astrophysics at the University of Nova Gorica. And today I'll be talking a little bit about what I've done in the last couple of months. So I've been doing this student project, which was a part of Inspiro, and it was covered by the funds of the Ministry of Education, Science and Sport of the Republic of Slovenia. And I did it at my university in the laboratory of the Materials Research Laboratory and Laboratory of Quantum Optics. So what I've done, I studied this molecule called BODIPY. And this molecule is a recently new molecule since it was first isolated in 2009. On this image on the right, you can see a simple version of the BODIPY molecule. And this molecule has fluorescent properties. And BODIPY is actually an abbreviation for boron dipyromethane. And it is also very rich in chemistry derivatives. So you can see on this new picture that you can change functional groups of the BODIPY, and by that you can tune the optical properties. So you can see by changing these groups, the BODIPY is fluorescent in different colors. It's been researched because it can be useful in light harvesting, so for making photovoltaics. It is also very used in biology and chemistry for protein labeling. And recently, the very new thing is photodynamic therapy, which is basically, so a patient takes in a drug, and this drug is then absorbed by cancer cells. And later on, when it's absorbed, the patient is exposed to some sort of radiation, for example, laser light or LED light. And then this drug is activated and kills the cancer cells. So this is a recently new field in which researchers find BODIPY to be quite useful. So I studied two types of BODIPY molecules. The first one was purchased by my university from Porfichem, SAS, France. And the other one was synthesized at the Ruđer Bošković Institute in Zagreb by the group of Nikola Basarić. So you can see, maybe we can point out that there is the big difference between those two is the ions on the right one. And the goal of my project was to investigate electronic properties of these two molecules. So how I did that? Well, the BODIPY molecule came in the form of a powder, and therefore I had to make a solution to make a thin film of it. And for solution, we chose methanol. Based on previous papers, it was found to be quite well. And so we prepared a solution of 0.025 liters with the 5.3 micrograms or milligrams of the molecule. And the substrate we used was a silicon substrate of 5 by 5 millimeters, and it had a layer of polycrystalline gold that was had a thickness of 20 nanometers. And basically, when this solution was prepared, we put the substrate in a device called the spin coater. So this device is shown on the picture on the right. It has a vacuum tube on which you put a substrate, and it sucks it in, so like it keeps it still while the spin coater is spinning. And then I took a particular volume of the solution with a micropipette, and then when it was spinning, I deposited it on the substrate. And we had 2 rounds of sample preparation, and to see which volumes and how much time we need to make a good, how much time does it have to rotate so that the sample is nicely distributed. And later on, with the samples from the first run, we did scanning electron microscopy. So the scanning electron microscope is a microscope that has a focus beam of electrons, and this beam scans over the specimen. And then the interaction of the surface with the beam produces backscattering electrons, and therefore when we detect them, the image is formed. So on this next slide, you will see the images we got from the scanning electron microscope. So on all of these images, you can see this spread out granulated structure, and that is the film, so the thin film of the BODIPY molecule. And also you might ask yourself, what's with the methanol from the solution? Well, it evaporated during the spin coating, so we were only left with the layer of the molecule. And well, you can see some interesting pictures here. For example, these white dots, white like blobs, and these are thought to be some sort of dust particles that fell onto the sample. On the second picture on the top, you can see this sort of a splash, and you can conclude from it that this BODIPY molecule was not nicely distributed, since we have the splashes from the depositing the solution with the micropipette on the substrate. And on the image below that, you can see some dark features, and we think that those are the aggregates of the molecule which are got charged during the microscopy. And on the picture right to it, you can see again these white features, and you can see a crack on the substrate. And maybe if you look close enough, you can see this darker square in the center, which is basically, let's say, it's a damage from the electron beam. And this same microscope has also the energy dispersive X-ray spectroscopy. So what does it do? You have the beam of electrons again, and it's shown on the sample. Then this beam of electrons knocks out core electrons from the material, and by that it opens up a space for an electron of higher energy to fill in. During this process, X-rays will be emitted, and they will have distinctive energy values for each element. And you can see on the next slide, these are the maps of the molecule thin film. So we did the scanning electron microscopy and EDX on the film prepared from the molecule that was bought. On these maps, you can see the distribution of fluor, nitrogen, and carbon and boron. Because I put them because those are the characteristic elements for this particular BODIPY molecule. And you can see that they are very nicely and homogeneously distributed over the surface of the sample. On this slide, there is a graph of the same thing as before. So on the y-axis, you have counts per second in electron volts, and on the x-axis you have energy in kilo-electron-volts. So we can see strong peaks on the silicon and on gold, because of course it was expected since that was the substrate. Then we also have peaks from boron, carbon, nitrogen, and oxygen, and fluor, which is also very good since those are the elements we expected. And you can also see some peaks for titanium, and we think those might be some impurities on the substrate. Then the final step was of studying the electronic properties of the thin film. It was done using the ultra-phased laser system CTUS at the Laboratory of Quantum Optics at my university. So you can see the scheme of the laser. So it's a titanium sapphire laser, and here the micro oscillator is the source. Then it goes through an amplifier, which was shown on this picture here, the green glowing. And then it gets split into OPA, which is the optical parametric amplifier, which then can generate wavelengths from 230 to 3000 nanometers, and also from the beam splitter it separates to high harmonics generator. And after the OPA, it goes to basically to the experimental chamber where the sample is kept. Okay, so how we investigated these electronic properties of the thin film. We used the method called photoemission spectroscopy. So this method relies on the photoelectric effect. In the photoelectric effect, we have some incident light shining on a material, and then these electrons are ejected or emitted from the surface, and they're called photoelectrons. And it works. It follows the conservation of energy, which is shown down here. So the kinetic energy is equal to the energy of the incident photon minus the work function minus the binding energy of the material. And the idea is to create this, let's say, a map, this energy map, and by that study the electronic properties. And so these are the results of the photoemission. On the first two images from the right on the bottom, you can see the energy spectra for the BOT molecule, and the last one is the one synthesized at the Ruđer-Bošković Institute. And then we can go to theoretical papers and look at theoretical predictions for a single molecule, and by that assign different parts of the spectra to different elements. And here there are some differences between the theoretical graphs and the ones we got, because first of all, the theoretical predictions are for a single BODIPY molecule, and what we got is for the thin film. And also the photon energy also affects how the spectra looks like. The other thing is that we turned the laser pump on and off, so to excite and probe the film. And on this graph on the left, you can see in blue is the BODIPY laser off, the pump laser is off, and then the pump laser was turned on. And we can see this activation in the region of floor. And after that, the pump laser was turned off, and it came back to its previous state. And so with this, you can see that the sample was not damaged since it came back, which is very good. And essentially, on the right, you can see a Jablonski diagram for the BODIPY molecule, and the Jablonski diagram shows basically the energy states and the transitions between them in a molecule, and we can see it's very complicated. So we still have some work to do. We have to do pump probe spectroscopy on the sample, and excited at different pump wavelengths. But the good thing is that we learned how to prepare a good thin film, since for the molecule that was synthesized at the Ruđer Bošković Institute, the solution was deposited on the substrate before the spin coating, which then left splash marks over the sample. And the right way to do it is to deposit it while the substrate is spinning. Also, we managed to do preliminary characterization with photoelectron spectroscopy, and we managed to assign different elements to different structures. And as I've shown on some slide before, we did the pump laser on pump laser off spectra, and there was an effect from this, and it didn't damage the thin film, which then gives the green light to continue during the pump probe spectroscopy. So in the end, I would like to thank all of the people all of the people that helped me do this project. These are the members of the Laboratory of Quantum Optics at my university, with the head of the laboratory, Professor Giovanni Danino, the group of Materials Research Laboratory at my university, then the employees of the Institute for Physics in Zagreb, and the laboratory IOM of CNR in Trieste, Italy. With that, I am concluding my presentation. I'm very grateful for this opportunity to present to you. And as I've said already, we still have some work to do. We're not finished with the project, but I'm looking forward to it. And that would be it for me. And then we can go to some questions if you want.